Okay. Okay, so this is the part of the show where I calm everyone down from the last one. So more of a technical presentation, hopefully not too controversial. So I'm Marc Levy. I work with Cobalt and Macnica. And the green button doesn't work. Oh, the big green button, sorry. Okay, so topics for discussion. Some more depth on IPMX timing. Again, a bit more depth on RTCP sender reports, and then a bit more discussion on forward error correction. Okay, so IPMX packet timing. So there's two parts really to IPMX timing. The first part is packet timing, and that's based on the 2110-21 standard. So there's two pieces to that standard that you have to comply with as a sender, and they're based on receiver models. The first one is the Cmax value. So the Cmax value really determines how many packets you can burst. So if you want to do a software sender, you want to be able to burst more packets. If you're doing a hardware sender, you can control things much more accurately. So what we wanted to do was we wanted to have something very similar to the wide model for Cmax, so that we can burst a larger block of packets every time. And it's still small enough that it's not going to overflow switch buffers, etc. The second part of it is not the same as the wide format for 2110, and so there's a couple of exceptions to that. And the reason for these exceptions is that we want to be able to limit the size of the buffers in the receiver so we can have low-cost implementations. Obviously, with 2110 targeting the Pro AV market, we want to keep the cost down. So really the difference there is that we've got a VRX buffer full, which is twice the Cmax value, which if you look at the top part, the Cmax value is typically going to be 16, which means that your VRX full is typically going to be 32, whereas if you look at the wide format for 2110, it's typically 720, which is a much larger receive buffer. So we're trying to kind of get the best of both worlds. We're trying to make software senders easier with smaller bursts, and we're trying to limit the size of the buffer in the receiver and make it still work. Obviously, if you're doing IPMX equipment, you're going to be looking at 2110 as a standard, so you still have the option of doing of making your sender narrow compatible, and that's certainly easy enough to do with hardware-based senders. Okay, so the next part of IPMX timing, we're going to get into the different timing models. So I'll first talk about sources of delay. So there's a sender delay. Obviously, there's processing delays through your sender, especially when you have compression. But that's typically very small, and it's typically close to fixed. So we could consider that to be a fixed delay. Then you've got your network delay, which depends very much on your network. If you've got a complex switch network, you're going to get more delays. If it's a simple single switch LAN, you're going to have very small delays. And then the next part is your receiver delay. So like the sender, you're going to have some processing delays, some packetization delays. You're also going to have some kind of buffer which you can control. So you can read out of that buffer based on time labels so that you can synchronize streams across different receivers. And this is really, when we talk about the link offset attribute with 2110, that's really what we're talking about. So we have the same concept in IPMX. Okay, so then there's a couple of modes of operation. So if we look at IPMX, IPMX doesn't preclude the 2110 mode. 2110 mode is pretty strict. You have a PTP network. In 2110, you require a PTP network. All your senders must be PTP locked. All your timestamps must be PTP locked. All your receivers must be PTP locked. Everything plays out in a perfectly synchronized way, which is that's what the whole point of 2110 is. Okay, it worked that time. Okay, so this is really what it looks like. You have a PTP grandmaster, you have an IP switch, you have a synchronized camera, synchronized sender, synchronized receiver, and so you play out on a very fixed schedule. Your play out is gen locked based on whatever your presentation time or play out delay is, or link offset delay is. Then we get into IPMX with PTP, but with asynchronous sources. So think of plugging in a laptop with an HDMI port. It's not going to be a synchronized source. Or you have a couple of cameras in a room that are all pointing at the same subject. They're not going to be synchronized either if they're simple HDMI cameras. So then, what if we're doing a display wall or something? We want to be able to synchronize the receivers. or we want, well, you know, if we're playing out video from multiple cameras on multiple screens, we don't want the delay on those screens to be different, so that if their eye moves from one screen to the other, it's jarring because those screens are not synchronized. So in this case, we have PTP lock on the senders and the receivers, but not on the sources. You can still lock multiple receivers so that they're playing out with the same time of day delay, even if they're not playing out gen-locked video. So that image will appear on those screens at the same time for us visually, even if they're not gen-locked. And so what we have in that diagram is we have a PTP grandmaster. We have it looks the same as the previous one. Diagrams.net put the actor thing on there. I know we call it talent in this industry. But it's showing the two cameras showing the same source, and they're going to play out on those two screens at the same time, even if they're not gen-locked. Okay, then the last one is the low-cost IPMX option where someone plugs in a HDMI connector and they want as little delay from source to sync as possible. They also don't want to lose any frames. So in that case, nothing's PTP locked. So the sources are not PTP locked. There's no PTP on the network. Sources are asynchronous. It's not possible to have precise presentation time. If the network delays are small, it may be acceptable. If you've got large network delays, you're going to get, it's going to be visually not aligned. And that's this case. You can see on the switch, there's no PTP grandmaster. It's really a best effort to display that image as quickly as possible. It's also, if you were recording that video or that audio, you would not have any lost frames. Okay, then RTCP sender reports. Why do we need them? We don't have them in 2110. So the one thing is that they provide timing information for the asynchronous media streams. So they identify the IPMX timing mode. Firstly, it'll tell you whether the sources are synchronized or not. It'll tell you whether you're getting, whether your source is PTP locked, so that if you're a receiver and you're PTP locked, you can check, okay, the source is PTP locked, it's on the same PTP grandmaster as me, so I can expect to be able to synchronize or align these streams. What it'll also do is it'll provide you a regular snapshot of RTP time versus PTP time. To be compliant with RFC 3550, we have to RTP timestamp the streams based on the media clock. So if we have an asynchronous media clock, our RTP timestamps are going to be based on that clock and not on the PTP clock. So then if we have PTP in the system and we want to align those streams, we have to be able to understand what that difference is between those timestamps. And by sending regular RTCP sender reports, we get a view of what those timestamps are. Yeah, question? Clarifying question. Mm-hmm. Under ST2110, the timing on every packet within a video frame has to be the PTP time. So if you're compliant with ST2110 streams, you can't have that situation where RTP time is different than PTP time. So can you explain under which cases the RPT time would be different than the PTP time? Sure. So if you're in that first mode that I talked about, which is the 2110 compatible mode, where your sources are synchronized and everyone's synchronized to PTP, then it will follow 2110 exactly. And that's really the only mode that's supported by 2110. In that case, your RTP timestamps will be PTP aligned. Because your media clock is going to be synchronous to your PTP clock. So in that case, it's possible to align those RTP timestamps with PTP. If you're in a situation where your source is asynchronous, you're required by 3550 to timestamp based on the media clock. In that case, you cannot have synchronous RTP timestamps. So in that case, your timestamps will be, even if they initially aligned with PTP, they're going to drift from PTP. So that's where you need the RTCP sender reports to tell you what that difference is. Yeah, John.
I just wanted to mention that 2110 does allow asynchronous streams. it recommends that things all be locked and blah, 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 but even the original 2017 version of 2110 does allow for streams that are not locked to the house reference. And then in the 2022 or whatever year they were really published updates, we clarified and expanded the terminology that's used in the STPs to indicate the timing source, allowing even more expressivity of what the timing basis is, which doesn't need to be PTP everywhere. So that's the mechanism under which these streams are compatible with 2110, is that they are asynchronous, but that's okay as long as it's signaled in a reasonable way, which it is.
Okay, thank you. Oh, yeah. Do we have another question? No. Okay.
3550 does not require the media clock to be locked to the RTP timestamp to be locked to the media clock. Profile may require, but 3550 says it can be free running. In fact, with MPEG, the type 33, it's a free. It can be a free running 90 kilohertz clock. Nothing to do with not synchronized. So it's not a 3550 requirement.
Okay, yeah, that actually that discussion did come up quite a bit, and it seems that a lot of the players that play out those RTP timestamps do require that the RTP timestamp update at a regular enough interval. So we just decided that it was better to, even though maybe it's not a strict requirement, there was some discussion around that. We decided to just have it follow the media clock and then use RTCP sender reports to allow you to adjust the timestamps. Okay. Okay, thanks for the clarification. Okay. Then the second part is, I thought this was going to be uncontroversial, but anyway. Everyone's just wound up from the last presentation. Okay, so the second part of RTCP sender reports is that they provide essence parameters. So it'll tell you what the video mode is, it'll tell you what the color space is, whether it's got, whether it's HDR or SDR, etc. Same with audio, and it'll also provide the block count, which lets you detect that and not forward bad information. So if you get a mode change that comes into your system, at least the RTCP sender report will, through the block ID, will tell you, okay, it's changed, you can stop, you can block your output, and then you can reconfigure your receiver to handle that new mode. So that allows the streams to really become truly dynamic and self-describing. Okay, so now we get into RTCP sender reports. So first comment is RTCP sender reports are required for IPMX senders. So if you want to put that IPMX label on your equipment, your sender has to send those IPMX sender reports. Those RTCP sender reports. This came up in Jed's presentation as well, but the sender reports need to be on the same IP multicast address with a UDP port +1. For video and ancillary, it's really field and frame aligned. For audio, it's as close to 10 milliseconds as possible, depending on your sample rate and whether you're 1 millisecond or 125 microseconds. Like I mentioned, block change indicates that your media has changed. Your RTCP sender report is always required to precede the change. So if your audio changes or your video changes, you will always see the RTCP sender report before the changed media. Okay. I'm not going to talk about this. This is really just an eye chart of what it looks like. I think what you can see from this diagram is it's really easy to pass. Everything's the ordering of things is fixed by the IPMX standards. It's easy enough for parsing in software. You could even do some parsing in hardware if you wanted to. So that makes it, certainly a lot easier than dealing with STP files. This is again the video info block for reference. Again, everything, there are text strings in there, but everything's laid out in a very organized fashion. So then, RTCP sender reports for clock recovery. So we talked about a couple of different modes of clock recovery. So the RTCP sender reports identifies the grandmaster. It also identifies whether it's, if it's not, basically whether the grandmaster is locked to GPS or not. So you get good information about the way that you can use that PTP grandmaster. If it's traceable, I think that's the term. So if it's traceable, then it's GPS locked, even if it's not on the same grandmaster. So if it's on the same grandmaster and it's on the same LAN, then you can typically use PTP for clock recovery. If it's on a different network, or it's a different grandmaster, but it's GPS locked, you can maybe use the timestamps, but you may not get as good lock for your media clock using PTP. So it gives you all that information. If you're in 2110 mode where everything's locked together, then you can really use your PTP clock to recover clock. You don't really need to be looking at the media. If you've got asynchronous sources with no PTP, then you really have to do media clock recovery. It'll still give you information about network jitter. So it's very helpful for clock recovery, but you still need to do media clock recovery. So the only case where you don't need to do media clock recovery is the full synchronous case. Okay. Now I'm going to move on to forward error correction. So forward error correction is optional. It's based on the 2022-5 standard. So IPMX doesn't preclude 2022-7. You can still do 2022-7 with IPMX. We decided to add forward error correction back in because forward error correction effectively disappeared from 2110. It was still there as an option, but no one really did it. And for IPMX, we decided that forward error correction was a good idea because we were wanting to be operating on lower cost networks. We don't necessarily want to have a red and a blue network. We're also, a lot of the time, we're operating over copper cables, so we're a little more susceptible to electrical noise. So we thought forward error correction was a good option to provide and to standardize. So what we have is currently we only have a profile A, and we may not ever have other profiles. Profile A has different matrix sizes for video and audio. So for video, we have a 2x16 matrix, and for audio, we have a 1x1 matrix. So audio is effectively redundant. Only column FEC is implemented. So from the people who remember the original 2022-5 implementations with 2022-6, there was always row and column forward error correction. For IPMX, we only define column FEC. The other difference is that for video FEC, the FEC matrices are always video frame aligned. So at the start of every frame, you're always going to be in the first position on the matrix. The way this works is at the end of the video frame, you can have a partial matrix or a terminated matrix. And if you read carefully in the 2022-5 spec, you'll see that that's perfectly allowable. There's nothing that stops you from having partial matrices. The other thing that you can do is if you've got variable bitrate compressed video, you may want to have constant latency, so you may want to terminate your matrices early. You don't want to wait for that matrix to fill up when you've got very slow portion of that variable bitrate video. So that's the other case that you can terminate. So this is just a diagram of the two matrices that we've defined. So we didn't define ancillary specifically, but that would, because of the low bitrate, would use the same as audio. So audio is really considered to be the low bitrate FEC matrix, and video has been the relatively high bitrate FEC matrix. Okay, so how does it work? It's an XOR-based forward error correction. By having column FEC over two columns, you can get a loss that covers two packets. So it may start at the end of one packet and spill over into the beginning of the next packet. In those cases, your forward error correction will cover those two packets. So you'll be able to recover those two packets and without any losses. Obviously, if you have a correction that covers 3 packets, then you're not going to be able to correct that. So this is a diagram which shows the traffic shaping, and it shows the idea of a partial FEC matrix. So we have time going down and to the right. So as those FEC matrices get sent, at certain points in the FEC matrix, you're going to send a FEC packet from the previous matrix. So I know it's really small. I can't even see it on the screen over here. But the matrices that are being sent alongside the media are actually covering packets from the previous matrix. And you'll see to the right, the two FEC packets that are getting sent cover the full matrix and the partial matrix from the end of a frame. So essentially those last two FEC packets are during vertical blanking time, and they're covering the last two matrices of the packet, of the frame, and the last matrix of the frame has been terminated because we just didn't have any more media packets. So your traffic shaping is very consistent. Obviously, if there's no media packets, you don't send a FEC packet, but provided there are, you're going to send them based on that traffic shaping. FEC latency. So, one of the downsides of forward error correction is it adds latency, because you're always sending FEC packets with the next matrix, and you're doing that so that your burst losses don't cover your FEC packets. So you get a burst loss, and then your FEC packet is going to be later in time so that you can do that correction. Because of the size of the matrix and because of the layout of the traffic shaping of the FEC packets, your video FEC is going to be at least 50 datagrams or packets. So there's going to be some processing delay for FEC as well, so you've got 50 packets plus some delay. So FEC latency, we have an optional SDP file parameter which can specify forward error correction latency, so that can be helpful. And the reason that FEC latency changes is obviously it's a function of your bit rate. So if you're in high bit rate, the higher your bit rate is, the lower your latency is going to be. What we have specified for audio FEC is that for all audio modes, the minimum latency is 100 microseconds. In other words, you can send that audio packet 100 microseconds after the media packet every time, regardless of what the audio mode is. And that's it. Any questions? I say.
All right, here comes